welcome back to my next video. It's been a while since I put out one, since the last one on linear regression. So I decided to do PCA, and I am going to assume for this video you have some basic understanding of linear algebra, how to compute eigenvalues, eigenvectors, you know how to find mean, standard deviation, and you know what all those terms mean. With that out of the way, what I want to do in this video is take a look at this example we have over here, this very small data set. And what we're going to do is we're going to, well, to the best of our ability, perform principal component analysis on this very small data set that we have. And then we are going to code up this algorithm in Python using only NumPy and very standard Python libraries, and then we're going to compare our results, our manual results, the result we get when we code it up, and sklearn's results. I think that's a very interesting way to learn. So why I chose this very small data set is just because, well, it's good to have like a understanding of what's going on with this algorithm on a small scale. So that way you can have an understanding of what goes on in a larger scale too, and hopefully by doing PCA manually, it'll demystify some of the confusion that you may have about some of the mathematics behind here. Okay, with that out of the way, let's get started. So what is principal component analysis? It is a method for reducing the dimensionality of a dataset by identifying the most important features, or principal components. And the important thing about these principal components is that they capture the most variance in the data. This is very useful when you're dealing with like very high dimensional data sets where there are many features, variables, and it can be very difficult to extract meaningful insights or patterns. And you can also use it for data visualization. So let's say you have a very high dimensional data set, and by reducing the dimensionality to just a few principal components, we can plot the data in a lower dimensional space, and we can get a better understanding of the relationships between the variables. And on that note, I want to make a note that there are limitations and drawbacks to PCA. It is not just some sort of silver bullet that will work on any data set. In fact, sometimes if you use PCA on your data set, it might actually lead to your machine learning model to have worse results. Since PCA assumes that the data is linearly related, and it may not work well if there are nonlinear relationships. And also, another key issue with PCA is that the interpretation of the principal components can be very difficult if there are many variables involved. So if you really want to understand your variables and you want interpretability, oh my god, I can't speak today, then you want to avoid using PCA, since interpretation is a big issue when using PCA. Okay, with that, let's get started on this example. So this is just 5x4 matrix, a data set. And so for this purpose, we're going to assume that, or we're going to treat each row as a data, and then each column as a feature. So this is feature 1, feature 2, feature 3, feature 4. And I just made up a bunch of numbers, but this still ends up working out. So what we want to first do is standardize our data. And well, why do we want to standardize our data? So let's say that your features have a very wide range, like from like 0 to 1,000,000, and it's all over the place. And maybe even, or even worse, your data is using different scales, right? Like maybe some is using millimeters, some is using centimeters, meters, or whatnot. And well, whatever the case, standardizing your data puts them on the same scale. And so that way, each data point will be equally weighted, or so to speak, and we are using this data set to feed into a machine learning algorithm. Okay. So how do we standardize our data? So let's take a look at the top right over here, this z value. So standardizing our data is taking each of these data points, subtracting it by the mean of our features, and divide it by the standard deviation of our features as well. So let's go ahead and just do the mean and the standard deviation of the first feature. Okay, so for the mean of the first feature, what do we have? Well, this is 2 plus 3 plus 3 plus 4 plus 1 divided by 5. And I am going to use mu to denote the mean or average. So, okay, this would go 2.6. Okay, well, let's calculate standard deviation. So standard deviation, at least for the first feature, right? Standard deviation of the first feature is going to be, well, let's take the square root. Actually, I'll write that square root in later. So we're going to take each individual data in this feature, and then we're going to subtract it by the mean, square it, and divide it by 5, take the square root, and call it a day. So we're going to have 2 minus 2.6 squared plus 3 minus 2.6 squared, and then we're going to do that for 3, and then 4, and then lastly, we're going to do that for 1 minus 2.6 squared, and then we divide that by 5. And I know, depending on the size of your data set, or whether or not you're come from statistics, you may be using n-1 instead of n to account for the fact that we used n when calculating the mean, the sample statistics. So you might, but I think from my experience, when you have very large data sets, using n doesn't matter. But when you have a smaller data set like this, maybe you might want to use n-1 and to compute the population statistic to offset the bias. Okay, and then we are going to take the square root of that. And then that should get us 1.019. Okay, so the standard deviation is equal to 1.019. Okay, well, if we do that for every feature, then what we're going to have in order is 3.2. This is also going to be 3.2 and 4. And then the standard deviation of the second feature is 1.6. The standard deviation of the third feature is 2.56 and 2.19 and so forth. So what we're going to do now to standardize this is we're going to take each of these variables, or well, each of these numerical values, each of our data, and then we're going to subtract it by the mean of its feature divided by the standard deviation. And if we do that, we are going to be left with this. So, all right. So what I'm going to do next is label each of these as F1, F2, F3, F4, and in a moment, you're going to see why. So what we want to do next is compute the covariance matrix. And so we really want to understand how each variable is related. And the covariance matrix is going to tell us that. So how do we calculate the covariance? Okay, so from here, this is essentially what we're going to be doing with each data point. And you may notice that I have left out, there's a fifth row of data that's left out. But that's because when a covariance matrix is going to always be a square matrix, and we're only going to use the size of it is only going to be the amount of features it has. So if it has n features, then regardless of how many rows of data, then your covariance matrix will be n by n. And I made a note up here in case you may have forgotten from statistics that the covariance between a variable and itself, it's just the variance. Okay, so let me also write down this formula that I forgot to write down. So how to calculate the covariance, what we're actually going to do is sum up all the xi's and then the yi's divided by n. And then also variance of x is just going to be xi minus x squared over n. Okay, so with that, let's do a couple of examples. Okay, so I'm going to be using values from this covariance matrix, not covariance matrix, the standard matrix that we standardized. Okay, so let's go ahead and do that right now. So, well, let's just first do the first two cells over here, and then we'll see. All right. So variance of f1. So, well, what did we have? If we still remember from our matrix, right? So actually, let me do it on this slide. I think that might actually make it easier to see. So there's no going back and forth. So, all right, let me use a black ink for this one. So for the covariance matrix, our standard matrix, we are going to be ignoring this. So let's go ahead and calculate variance of f1. So variance of f1 is going to be 0.588 squared plus 0.392 squared, and then actually, let's not be lazy. There's only two more data points here. Oh, no, that's not a negative, that's a positive. 372 squared. And that is divided by 4. All right. So let's check. Okay, just checking the covariance formula. Okay, so the covariance between F2 and F1 now is going to be negative 0.588. And, well, if we look in our formula over here, well, the mean of each variable is just going to be 0, right? Because when we standardize our data, we're going to have a mean of 0 and a standard deviation of 1. I think I should have mentioned that a lot earlier, but that's okay. 392 over negative 0.75, and then we're going to do the same thing over here, 0.392, and then that's going to be 0.5, and then we're going to plus 1.372 and negative 0.75, and then all that divided by 4. Okay, and well, if we take these values that we calculated, the first two values should be 1.25 and negative 0.245 respectively. And if we do that for all the other values, then we're going to get this matrix. So this right here is going to be our covariance matrix. This is our covariance matrix. And so for each of this tells us the relationship between F2, F1, F3, F1, F4, and F1, and so forth. All right, so what is the next step? So the next step is calculating the eigenvalues and the eigenvectors of this matrix. So just as a refresher, eigenvalues and eigenvectors, when we calculate them, we're going to be using this AV equals lambda V, where lambda is your eigenvalue and V is your eigenvector. So what does this mean? Well, you notice the V's on both sides, right? So it's just saying that when we have some vector and A is our data, it's like when we apply this transformation, this linear transformation to V, we want to find the vector that does not change direction. And it doesn't change direction, but it may stretch or shrink. And the factor which it stretches or shrinks by is our eigenvalue, right? So how do we calculate the eigenvalue? So we calculate the eigenvalue by subtracting lambda from its diagonals, calculating the determinant of that matrix, and then setting that equal to 0. And you're going to be solving that like quadratic, maybe a cubic, a quartic, whatever. And then for the eigenvector, Well, for each eigenvalue that we have calculated, then we're going to subtract that from its diagonals, and then we're going to add this vector v to it, and we're going to solve it like a system of equations. So let me give you an example. So one of the things that we just mentioned is when we're doing the eigenvalue, we're going to be subtracting this lambda from its diagonal. So this is what we're going to do. We're going to subtract the lambda from its diagonals. And we're going to compute the determinant of this 4x4 matrix, which I assume you guys are familiar with determinants. So when we compute our determinants, got a little ahead of myself over there. So let me just go back. When we compute our determinants, we're going to get 4 eigenvalues because we're going to be solving a 4th order equation. So here are the eigenvalues I got, and feel free to work along to make sure that you are getting the same things that I am. And if there are any mistakes that I have made, let me know in the comment section below. But I have done these calculations multiple times to make sure that there are no errors. But hopefully I didn't make any mistakes. Well, yeah, this is what I have. So what we're going to do is when we pick our principal components, so the top principal components, we are going to pick the ones with the largest eigenvalues. And this just means that these are the eigenvalues, and the eigenvectors it corresponds to can have the largest percentage of variance explained. So if we wanted to pick the top 3 principal components, we'll pick these. But for our purposes, let's take n equals 2 principal components. Principal components. Okay. So remember what I said about subtracting each diagonal by the eigenvalues. So for each eigenvalue, what are we going to do? Well, we're going to subtract, if we subtract this 1.25 by lambda 1, well, by 2.65, we're going to be left with this. Right? So, and to calculate this eigenvector, this v1, v2, v3, v4, this is essentially a system of equations, right? So we're going to be solving for something like v1 minus negative 0.45 v2 minus 1.11 v3 plus 0.224 v4 equals 0, and so on, right? So we're going to have 4 equations and 4 unknowns, and you're going to be solving for that. And there are many different ways. You can use Gaussian elimination, you can use Cramer's rule, and you can use Wolfram or whatever to help you. But when I computed the eigenvectors for this using Wolfram, the corresponding eigenvalue, or the eigenvector to this I got was, well, this eigenvector corresponding to the eigenvalue of 2.65, I got negative 0.519. And remember that I am rounding a lot of this stuff. So when we plug this into Python later, our results might be off just a little bit, but that's okay. Okay, so this is the eigenvector corresponding to the eigenvalue of 2.65. So that is our first principal component. So our second principal component, we have an eigenvalue of 2.123, and likewise, when we compute the system of equations for this particular system, and using Cramer's rule, Gaussian elimination, whatever, then you are going to get the eigenvector of negative 0.470, negative 0.502, 0.571, 0.449. Okay. So one of the things I want to mention before going forward is that this covariance matrix that we calculated, this covariance matrix right here is considered ill-conditioned. So what that means is if we want to solve for the eigenvalues and eigenvectors depending on the type of numerical method you use or your library uses, you may have drastically different results. So since it's ill-conditioned, it means that small changes in your input will result to drastically large changes in your output as well. And when I computed the condition number of this matrix, it was like 22,000 or something. And even a condition number of 1,000 is considered numerically unstable. Okay, so going back, so we have computed our principal components. We have our first, this is eigenvector 1, this is eigenvector 2. So, but we haven't done anything to our original data yet, right? So that's what we're going to do now. So what is this data set? This data set was our standardized data set, right? Standardized data set. Standardized D, and then if we look on the matrix that's being multiplied on the right, this was just our eigenvector corresponding to our eigenvalue of 2.56 eigenvector, right? Eigenvector. And then this eigenvector is just the eigenvalue corresponding to, whoops, let me rewrite that, eigenvalue of 2.123. This is its eigenvector. So what we're going to do is we are going to multiply this, and this matrix multiplication. Hopefully you understand how to do that. And if we do that, then voila, this is going to be our data set after we apply principal component analysis on it. Okay, let's get on with the coding portion. So one of the things that we're going to do is import the NumPy library and define a PCA function. And PCA is going to intake X, our data, and K, which is the number of principal components that we will specify. So I also did an outline over here of what our steps were from what we did when calculating it by hand. And we standardized the data, computed the covariance matrix, and using the covariance matrix, compute the eigenvalues, eigenvectors. We sorted the eigenvalues and eigenvectors in descending order of eigenvalues, so we can take the top k principal components, or the top k eigenvectors, and then we transform the data by multiplying the standardized data by our top k eigenvectors. And then afterwards, what we're going to do is let's return, well, in order, we're going to return our eigenvectors, eigenvalues, and then our transformed data, okay? All right, let's start with the first one. Well, standardizing the data, X standard. We're just going to take our data, subtract it by the mean along the axis equals 0. That's just saying that, okay, our columns, each of our features is indicated by columns, right? So each row is an observation. And then we divide that by the standard deviation of X. Same thing, axis equals 0. And we can compute the covariance matrix in NumPy just using this. So covariance matrix is going to be mp.cov of X standard. And what we want to do is specify this row var equals false, because otherwise it's going to it's not going to treat each of our rows as observations or our columns as features. So if that's the way your data is structured, where each of your individual rows are your observations and your columns are features, you want to set row var equals false. Okay, so now let's compute the eigenvectors and eigenvalues by using numpy.linalg.eig of the covariance matrix. And what this does is it returns a tuple of eigenvalues and eigenvectors respectively. So there you go. So that's, we can get our eigenvalues and eigenvectors just like this. Okay, so what we want to know now is we want to sort the eigenvalues and eigenvectors in descending order of eigenvalues, right? So let's just access the index first. So let's take the arguments that would make the eigenvalues in descending order. And this is what we will do. So we're going to do arg sort -1. Okay. So this gives us the indexes. This gives us the index says of the eigenvalues in descending order. Okay, so looks like I might have, oh, whoops, made a mild error here. So boom, done. Okay, so next our eigenvalues are going to be in descending order based on our indexing here. And then same thing with our eigenvectors. We're going to eigenvectors. And the way we're going to splice this is, okay, we're going to take everything. And for the columns, we're going to take the columns in descending order. Okay, so how are we going to take the top k eigenvectors? Well, the top k eigenvectors are just going to be everything here. We want everything except we want the top k, and that's how we index that in Python. Okay, so the next thing to do is transform the data by multiplying the standardized data by our top k eigenvectors. Okay, let's do that. So let's say x PCA is going to be equal to NumPy, dot matmul of x standard and eigenvectors. Okay, so let's go ahead and do this, and we're going to return eigenvectors. And what we actually want to do is transpose this. I mean, it's not like a really huge deal, but it's just in data science, it's just common to represent our vectors in rows instead of columns. So that's what we'll do. So, and then we return the top k eigenvalues, and then we return our transformed. Okay, let's go ahead and do that. Okay, what better way to test our function than on the data that we had in the beginning of the video? So I'm going to copy and paste that as a NumPy array over here. And let's go ahead and call the PCA function that we wrote on the data. And we're going to specify two principal components. All right. Wow, everything looks pretty good. So our eigenvalues and eigenvectors that we got are almost exact. So let's take a moment to dissect this. So the second array that we returned was our eigenvalues, and in descending orders 2.65 and 2.123. Okay, let me take a look at my notes over here real quick and just to compare. And yeah, so that's the eigenvalue I got using external calculator. I also use Wolfram to help me out with the calculations. And what about our eigenvectors? So this is our first eigenvector, and that looks like almost exact, and so does the second one. The only thing that I have that is different is the first row over here. It looks like this we got negative 1.95 and negative 1.72, and theirs is well, this one is a little bit lower, and this one is a little bit lower as well. Oh, sorry, this one is a little bit higher, this one's a little bit lower, but doesn't look like it's off by much. Remember, I also mentioned that our covariance matrix was ill-conditioned, so small changes in the input could lead to very large changes in the output. And in our example that we did by hand, I did do a lot of rounding, so this could be attributed to that. Okay, so let's go ahead and actually check out the sklearn's PCA library. Okay, I just want to make a note that if you import this like this, then what's actually going to happen is this PCA over here is going to rewrite our PCA function. So I just want to make sure we're aware of that. So this data isn't, or at least PCA doesn't standardize our data for us. So what we're going to do is we're just going to do it ourselves, and that's not too bad. It's just a one-liner, and divide it by numpy.std of data x equals 0. Okay, perfect. And then here we can call a variable PCA, and we are going to specify two principal components, and then we are also going to do PCA.fit onto our data. Okay, and then after that, let's look at some of the info. So let's print out, so this is the eigenvectors. So we get the eigenvectors by doing this. So there's the eigenvectors, and then let's also print out the eigenvalues eigenvalues, and that's in PCA.explain variance. And I'll get into a little bit of what this means in a little bit, but that's the way to print out your eigenvalues. Okay, so what about our transform data? To print out your transform data, we can do it like this: PCA.transform onto our data standard. Okay, let's see. Oh, I made a little output. Output looks a little funky, so let's go ahead and fix that real quick. So there you go. Perfect. Okay, so looks like our eigenvectors and our eigenvalues in our transform data almost match up like one-to-one. So like, yeah, everything looks pretty good. Okay, so another thing I want to mention, another feature that we can use is the explain variance ratio over here. And this is done by explained variance ratio. Okay, so this is the output. What does this mean? So remember in the beginning, I mentioned that we want to pick the top principal components that has the greatest variance, right? So what this means is that the first principal component, well, can explain about 53% of the variance in the data, and the second principal component can explain about 42.46 variance in the data. And how high you want this depends on you, but obviously the higher, the better. So that's just another cool feature that explain variance ratio has. So essentially we can interpret these eigenvalues as well. This 2.65 is 50% or 53% of the sum of the eigenvalues. So for example, if our eigenvalue was 10 and our total eigenvalue was 20, then, or the sum of our eigenvalues was 20, then that means that that principal component, the 10 divided by 20, will account for, or can explain 50% of the variance. Okay, well, that concludes our PCA video. Let me know if you have any questions down in the comments below, or if there was anything I might have missed, or if there was any mistakes I have made, so I can make a note of that. All right, thank you for watching.